Hi, and welcome to the next lecture in the series on Senior Maths B. This week we're looking at learning maths. Why this is important is this is really the bread and butter of our work. One time there was a story of a drill salesman who was interviewed about his success. He won numerous prizes for being a successful drill salesman, and they asked him why he was so successful. And he said the key to success was knowing your business. And so the interviewer said, "Oh, so you know everything about drills?" And the salesman replied, "No, I know everything about holes." Now it's a bit like that with us. We're in the business of teaching, but really teaching is only important because students are learning. And so our core business is about learning. We should know and understand about learning. If there is no learning, then we don't need any teachers. We only exist because in classrooms the students learning, and in our case they're learning about mathematics in the senior school. So that's the focus for today. Now, one of the most traditional approaches to teaching mathematics is based on behaviourism. What behaviourism really is an idea that if you create a set of inputs, you'll get responses from the students that can be fairly well predicted and programmed. And this is fairly common in the classrooms you'll see in maths around Australia and indeed around the world. What you'll often see is the teacher up the front who will give some notes or ideas, then do some worked examples, and then the students will practice from their textbook. Now, it's important to say there's nothing wrong with this at all. It's an important part of a balanced program. But if that's all we're doing, then we're only going to get a very narrow understanding of mathematics. In fact, what Skemp's called an instrumental understanding. And if you think back to the other week when we talked about the nature of mathematics, they're going to miss out on some of those parts of mathematics that exist that can't really be facilitated or learnt through this way. And it tends to help to create a situation where the students are more passive and just receive the knowledge rather than engaging with it and building it up for themselves. Now, like I said, it's an important part of a balanced maths program, but we should be doing more than just transmitting knowledge. The advantages of a behaviouristic type approach is often you can get to the answer more quickly, and sometimes the answer is important. But often if you think about the ideas we're teaching in Maths B, the answers really aren't that important. It's more some of the processes and thinking students will go through to get there. So it does reward the immediate and the apparent and the particular work of students that they produce on the spot. It's a narrow channel, if you like, which directs them to a specific goal, and from that position they can learn something quite precise. This is an important thing to be able to do. But it's not enough, because if we only have this, students will have a narrow understanding of mathematics. They'll have a good, possibly a good skill set, but they'll not be able to understand and apply their knowledge necessarily more widely. So this is why we need to develop what Skemp calls relational understanding. Now, relational understanding is a bit different because it promotes student understanding of the concepts. It's harder to achieve, it's more complex, it starts with what the children already know and understand and other things they bring to it. It's not such a narrow channel to put them through, but it's broader. And in this way, it can be more difficult to achieve. But the advantage of when we have pedagogies which help build relational understanding is the kids or the students can understand and apply that knowledge more widely, and particularly to unfamiliar contexts. They haven't learned just a narrow channel to run in, but they've learned some ideas which will help them can run in different channels. It's a bit like if you think you went to a new city and you wanted to tell someone how to get somewhere, you could give them the steps on the map to get to that one place, or you could teach them how to read a map and they could find a range of places. A good mathematics program is going to have times when students develop good relational understanding and good instrumental understanding. So the big question is, well, how do students learn maths? In particular, how do they learn maths in the senior school? Well, unfortunately, the disappointing answer is we really don't know. I did a study where I looked at 20 noted exceptional teachers of mathematics. And one of the first things that struck me as I went into each of these different classrooms was all of these teachers were different. Some were very formal with rows and columns, fairly didactic approach. Whereas other teachers were very informal, students were sitting in groups, they were noisier, and they were all seen as good teachers and they all got effective results in senior school maths. So in this course, I'm not going to give you a recipe. I'm going to give you some ideas, and you need to think about these in the context of your personality, your teaching approach, what you think works, and also the students you're working with. But the other thing that's important is what the students are learning. So if you're trying to teach them some sort of conceptually dense idea through a didactic, instrumental approach, it probably won't be very successful. In the same time, you don't want to use sort of a discovery approach to find something that might be quite precise at a procedure you want them to learn. So that's where you need the wisdom of teaching, and that's the art of teaching, knowing what and when and how to do different things. I'm going to give you a few practical ideas that are theoretically based, and you can see how they might apply in your situation. The first person I want to talk about is a theorist called Piaget, who has influenced education, and particularly mathematics education, for a long time. You may remember Piaget had a theory where students and children at various ages could do various things. So when they're very young, they needed concrete material, and as they got older, they could move on to abstract representations. Now, later on in his work, he decided that the idea of moving from concrete to abstract was important, but in fact, students don't change at different ages when they're capable of doing different things. So even older children sometimes need to work with more concrete representations. And even us as adults, when we learn something new, sometimes we need to start with something we can get our handle on more practical or more concrete or more visible before we move on to the abstractions. So rather than remembering Piaget as an ages and stages approach, I think we need to take the idea from Piaget that when we're introducing something new, we need something sort of concrete for students to put hang their handle on, try and get an idea of what they're talking about, to then move towards abstraction. So it's no good just leaving them in the concrete stage. Our job is to move them towards abstraction. And indeed, that's the power of mathematics. Particularly in senior maths, we can sometimes lose the students because we jump very quickly towards abstract representations. Rote learning is something which we've had a long time at maths at all levels, and we do it even at senior level. Now again, sometimes there's some things that students just need to memorise, but I'd argue that rote learning is not always the best way to do it. A key point here is that practice doesn't make perfect, practice makes permanent. And if you ever had the misfortune to come and play golf with me, you'll see I have a swing that I've practiced many, many times, and it has become permanent. And when I went, after playing golf for a little while, I thought, I quite enjoy this game, I'll go and get some lessons. The first thing my coach had to do was to unlearn my bad habits, so which had made permanent through my practice, so he could then teach me some correct techniques. So what are the implications of this? Well, first of all, we give students lots of mathematical exercises to do, which in a sense is a form of practice. But if we're going to give them mathematical exercises to do, it's important that they know what they're doing, because they'll practice these things and make them permanent. So if we give students exercise to practice before they have an understanding of what they're doing, you could make permanent bad habits. So the implication of that for the learning sequence: when do we give students exercises and get them to practice ideas and concepts and procedures which we've taught them? After they have some understanding of what they're doing. So when they practice, it's purposeful and it makes permanent something we want to be permanent. Interestingly, this has implications too for homework. There isn't a lot of evidence to say that homework is particularly helpful for students' learning, but we seem to love it in Australia and indeed in many countries around the world. But the point I'd make here is if you're going to give homework, make sure it's something the students understand and can do well. So when they go home and practice in an unsupervised manner, they're not making permanent bad habits. The next idea I'll quickly talk about is learning from experience. If you look at most of our lessons, it's made up of primarily creating certain experiences and activities for students to do. And these activities in and of themselves are quite valuable, but they're not learning themselves. What we need to do is help the students notice things and reflect on them, to note the things that are important. So John Mason coined the term noticing and noting. What do we want the kids to note, or the students, to notice in various activities, and then what do we want them to note? I'll give you an example. It's not enough just to have a good maths activity, you actually have to direct them towards something, and often that's the part we miss out as teachers. For example, here's two graphs we could have got the students to draw about translating functions. And you can see on one side we've got y equals x squared, and on the next side we've got y equals x squared plus 2. Now, I've often seen these drawn as we try and help students to understand the translations of graphs. But if we don't point out what the features we're trying to help them to see, they may not pick up the mathematical idea that's involved. And here it's the idea of the constant at the end shifting the graph up to 2 units. Now, these ideas we'll revisit later on in other lectures and activities as well. I want to give a little bit of an instructional model too, because a lot of the stuff in Maths B talks about applying to meaningful contexts. So if we do that, often what we see in the sequence of learning is, and particularly if you look in textbook exercises, they might have a whole range of exercises to practice, and then you get towards the end and it has 4 or 5 applied problems, as if these are the same as the ones they've been doing. And what we know is that often students can do the procedural ones, or they have the instrumental understanding, but then they get to the applications and they get a bit lost. So in this point, it's not enough just to teach them the procedures or the instrumental understanding and expect them then to be able to apply it in a relational way. So here's my suggestion. Like I said, this is how we often start. We teach a mathematical concept or idea, and then we hope they can apply it to a problem or a context later on. My suggestion is where you can, you start with a mathematical problem in context, try and generalise out the mathematical ideas, and then help them to apply it in another way. So for example, if you wanted the students to learn about integers, you might start with questions about temperature around the world. You then generalise so they're just talking about the numbers, you know, what's bigger, -1 or -5, and then you might apply that to different contexts, I don't know, my bank balance or something like that. The next thing is, very quickly, there's a lot of research about how our brains work, and I'm not going to go through all of that now, but interestingly, a few years ago, the National Councils of Teachers of Mathematics in America said, mathematics makes sense. All students must believe this, and all teachers must believe in their students, or that their students can understand this. Now, I mentioned this to some students one point, that mathematics makes sense, and they nearly laughed at me. So somewhere along the line, we're not getting that part where the students understand it, at least in my classes anyway. But I just want to talk very quickly about memory. I don't know if you've had the case where you've taught something to students, they come back the next day and you say, remember yesterday when we did such and such, and they say, no idea. So how does our memory work? Very simply, we've got something called immediate memory, which lasts for about 30 seconds. And then we have working memory, which lasts for about 10 to 20 minutes, depending on the age of the kids and other factors, the interest level. And then we have long-term storage. Now in a lesson, often what we try and do is a lot of work in working memory. Now incidentally, if we're still going after 40 minutes, you can see that a lot of the students have either had to delete some stuff out of that space because they can't cope with it anymore, or it's gone. What we need to do is try and get some things into long-term storage or long-term memory. And in simple terms, how do we do that? Well, there's 2 key things. There's explicit memory, which is experientially based. So for example, if you remember going back to school and your school social, you might be able to remember a song that was played, even though it was a one-hit wonder and you can never heard of it again. But it's experientially based. It's based in your memory based on a significant experience of your life, even a long time ago. And then we have implicit memory, which is automatic responses. For example, when you drive a car now, hopefully you're not thinking about what you're doing with your feet or something. All of that becomes automatic. But the key thing is, if we want knowledge to be stored in long-term memory, it must serve 2 criteria. It must make sense and it must be meaningful. And I think this has important implications for teaching mathematics. So the first one is, does it make sense? Can our learners in our Senior Maths B class understand the mathematical ideas? Now this can be difficult because the ideas in this level of course are quite difficult to understand and tricky. So the first thing is, does it make sense? And does it fit with what they already know? I remember I went into a class one time and a student asked another student who was talking to, and he says, I don't understand this. And the other student said, don't worry, we don't understand it, we just got to regurgitate it. Now, the point is, if you want them to regurgitate it, it's much more likely to happen if they understand it. The second thing is, does it have some meaning? Is it relevant to them in some ways? Again, I don't know about your classes, but when I maths classes, I often got asked, when am I ever going to use this? What do I need to know this for? And what I try to do is always have an answer for them, because if we can't answer this question, then they're going to struggle to remember it again because it just doesn't have any meaning to them. And an adequate answer isn't just you'll need it in the test in a couple of weeks. So try and give them a reason to remember it. It doesn't mean they're going to use it in their life, but it has to have some meaning somewhere. And the last point I want to talk about is developing mathematical identity. And what I mean by that is instead of just thinking about trying to put knowledge into kids' heads, we want to build knowledge in their heads, but we also want to give them some tools and skills to use, but we also want to somehow impact their attitudes towards mathematics and those sorts of things. For a long time, we've sort of neglected the attitudes part of learning mathematics, and we've unfortunately got a long history of kids who leave our classes who really don't like maths and don't want to have anything to do with it again. So this is a little picture that might help. If you think about the head, in the head we're trying to put knowledge and ideas and concepts, things that we've traditionally focused on. The things we haven't focused on, and we don't have to explicitly focus on the class, but through the way we run our classes, our relationships with the students, the way we connect the students to mathematics, they'll develop attitudes and values and dispositions about it as a subject. And finally, we want to give them some skills, which I've called the hand here. So can they factorise a quadratic equation or something like that? Here's a little quote from Piker Palmer. I quite like this. The teacher who knows their subject well must introduce it to the student in a way one would introduce a friend. The students must know why the teacher values the subject, how the subject has transformed the teacher's life, and by the same token, the teacher must value the students as potential friends. Be vulnerable to the way the students might transform the teacher's relationship with the subject, as well as be transformed. If I'm invited into a valued friendship between two people, I will not enter unless I feel like I'm valued as well. Now, all he's really saying here is when we come to teach mathematics to students, can we introduce it in a way that we're trying to help them to develop a new friendship with something? Because perhaps the biggest problem we've got with maths from senior school over many, many years across many states and countries is that kids can learn the knowledge, can develop some skills, and they can hate it so much they never want to go near it ever again. So how can we build this sort of bridge with the students? Well, this probably isn't rocket science, and if you've been teaching in the junior school for a while, you know that relationships are important. How kids develop attitudes towards maths is often grounded in their relationships they have with their teachers. And they're very powerful in that they can turn students onto maths or they can turn them completely off. I interviewed many students about maths, and whether they loved it or hated it, they almost always could tell me the teacher who turned them on or turned them off. It's a powerful position we have. The second thing is we need to have mathematical pedagogy that allows the students to experience the subject in some way that's useful and interesting and fascinating. And you may have heard that before last week. And we need a pedagogy that is indeed mathematical. So if students are just memorising things, then maybe they're not doing mathematics, they're just memorising random things that have little meaning to them.